What powers your telescope? When the public asks this question, it's most likely that they're thinking of magnifying power. This set of activities helps your visitors understand that the much more important power of a telescope is its ability to create a bright image with more detail. Brightness and detail are primarily based on a telescope's aperture, the diameter of the primary mirror lens, not the magnification you're using. The power that observers are concerned with is primarily the telescope's ability to collect a lot of light.
There's only so much light coming from an object every second. Little packets of light called photons. A galaxy outside the Milky Way is tremendously far away, and its light is spread out all over the universe. So only a little of its light, or its photons, hits the surface of the Earth. The more of its photons that we can collect, the more likely we are to see it. So, telescopes have big mirrors to collect more of these photons of light. Now, our eye needs about 500 photons, or packets of light, coming into it every second for our brains to sense that something's there. We'll use these grains to represent photons of light from a distant galaxy. We'll sprinkle these photons for 1 second on this area, okay? 1001. All right. Now, will our eye ever detect the light, do you think? How many photons are getting into our eye there, that pupil opening in the eye?
Not very many.
Not very many, right. Is that enough light for our brains to detect it?
You said you needed about 500.
That's right. Not enough, right? So, but is there enough light hitting this telescope mirror?
I think so.
Okay, good. But how are we going to get all of the light hitting this telescope mirror into our eye, right? Well, let's remove a strip of the telescope mirror. These sticks show the light from that distant galaxy reflecting off the telescope mirror. Okay? That's what these sticks represent.
I see.
Now, a telescope mirror is curved. So, when the light comes in, the mirror reflects it out, reflects the light back out to a point, like this. Now can we fit all the light into our eye?
Yes, we can.
Yeah, good.
How big are some of the telescopes NASA uses to study the universe? You'll be able to answer that question for your visitors with this activity.
Here we have a string that has markers marking the apertures of various telescopes NASA uses. The aperture is how big the telescope's light collecting area is. My telescope has a light collecting area 8 inches across. That's about this big. How big are telescopes NASA uses? Who wants to be at the center of these telescope light collecting areas?
I will.
Great. You hold on to that.
All right.
And why don't you hold on to the other end?
Okay.
Now, who has heard of the Hubble Space Telescope? Great. Why don't you hold on to the string right there where the Hubble is? The Hubble is out in space, going around the Earth. Now, who wants to draw the Chandra X-ray telescope? Okay, stand right there where the Chandra is. That telescope has discovered black holes in the middle of galaxies. And why don't you draw the Keck Astronomical Mirror? Astronomers have discovered planets around other stars with that telescope. Now, let's hold the string on the ground, and as the end moves and the center stays still, we'll make marks every couple of inches where our telescope is on the cement. Compared to my telescope, can the Hubble collect more or less light?
A lot more.
This activity can generate a lot of discussion, including how much more light one telescope can collect than another. For example, if we used 1 teaspoon of grains representing photons to cover the 8-inch telescope mirror, how many teaspoons do you think it will take to cover the Hubble's mirror? it would be about 100 teaspoons, or about 2 cups of grains. If doing this for a school group, you can have the kids calculate how much more surface area each telescope has, using the formula pi times the radius squared.